Welcome back to the second video of my manual file carving category in the digital forensic series. In this segment, I will cover a brief analysis of the data area, calculations to find the offset of particular locations of the image, and manual file carving. In the previous video, we've covered slides which contained information about parameters and limitations of the FAT16 file system, contents within a typical FAT file system, what slack space is, how to install Bless hex editor and set up the 16 bytes per row layout, how to install the sleuth kit, and we used a command called FAT16 to analyze the logical layout of the image that we're analyzing and extracted information necessary for this type of analysis. I highly urge you to watch my first video in the manual file carving category before watching this one, as it covers information which is incremental and you may struggle to understand this particular video without watching my first video. As I've mentioned in the previous video, our hypothetical scenario is that our department has taken a criminal into custody and have confiscated their USB flash drive containing sensitive data, which happens to be crucial to the investigation. Our job as a digital forensic analyzer is to extract all data contained on this USB by any means. I've forgotten to add a key element in the previous video about a hypothetical scenario, which is that the criminal has deleted the contents of the USB flash drive. So we're undeleting files to recover, as well as trying to rebuild the cluster chain in this category of videos. I'll leave a link to the image file that I'm analyzing in this scenario. I'll also leave timestamps for sections for this video, both of which can be found in the description. I forgot to mention that I am using Ubuntu version 18.04.3. You can download this from Ubuntu's website. Now, I've got the documents open here, which contains the logical information that we've retrieved about the image in the previous video. I'm just going to open FSStat in terminal again because I forgot to get these two bits of information, which is the sector size and the cluster size. These are crucial again for our calculations. So the calculations that we're going to do are going to help us navigate around the image. And there's two calculations we're going to be using. So these two are the ones. So this particular calculation we're going to be using to navigate around the image and find where the starting point of what we're looking for is located at. And this particular calculation will enable us to use the parameters of the 32 bytes of code in the FAT to be able to calculate the starting area of that particular file. So that way we can navigate around the image using these two calculations and extracting files. And our aim is to recover a non-deleted file, because at this stage that will be the main priority, because recovering deleted files will require you to rebuild the entire cluster chain, which will be covered in a later video. So I'm quickly going to show you what we're looking for again. So the primary and backup of the file allocation table is going to be in that area, and directly after that is going to be the data area. And what we're going to typically be doing is we're going to be using the parameters of what's given in our file allocation table area, using this formula to use the parameters in the 32 bytes of code, and then apply that with the target sector and the sector size to navigate to the data area. And that way we'll find the particular file. That's our aim, at least. And we're going to be using this template to identify what the attributes mean. And we're going to be looking at the attribute column, which is that byte there. And we're going to be comparing to see what's in that byte, depending on the hex mask. And that will give us an idea of what we're actually looking for. So before it gets too confusing, I'll just proceed. And that way you guys can actually visually see what's going on. So I'm going to open Bless hex editor again. So right now we're at the starting of the FAT16, and I've opened it from the results. So you can see that I'm using a duplicate copy as opposed to the original. So I've done all my preliminary checks to check if MD5 sum and all that match. And I've made a copy of the FAT16 lab. That way I'm only manipulating the copy instead of the original. So what we're gonna right now do is use this particular formula for navigation purposes, and use this particular formula for actually deconstructing attributes into a figure that we can use for navigation. So what we're going to do now is we're going to navigate to the data area. So we can see that the data area starts at 504. So that's going to be our target sector in this case. If we take 504 multiplied by the sector size, which is 512, that gives us 258048. Now, if we were to write this in hex, that would be 3F000. That base 16 represents a hex value. So this will then equal 0x. And note that when you're writing decimal and hexadecimal numbers together, to always write the hexadecimal numbers with their starting 0x to differentiate them. So 3F000. And if we were to navigate to this particular offset, you can do this by clicking on search and then clicking on go to offset. So it brings up this particular bar here. This bar may not be there for you. If you click search, then go to offset, or simply click Control G on your keyboard, and that way the offset bar comes along. That way, once we navigate to this particular figure here and scroll down a bit, you can see that at the 3F000 marker, because this is the root, this is where the data area starts, we can validate that this in fact will be the root of the USB. And how we can know that is by using the images that we were looking at before. So if we open these two particular images, we can see that the first two lines will be used against this template, which is a FAT directory entry. We're going to be looking at this attribute byte over here, which is 4 bytes from the right. 1, 2, 3, 4. That's the 08 marker. And if you look on this chart, a 08 stands for volume label. So that's how we come to know that this is the volume label. That's what the particular USB would be called, FAT16 lab. And we can validate this again by looking at the fstat output, which shows you the volume label of the root directory. So you can validate this information by, if you think you're not being in the correct place or anything like that, you can definitely validate information using other tools. So what we're going to do is right now I can see two directories just using the ASCII key viewer to the right. Everything that Bless Hex Editor registers as an ASCII key, it'll show us, or a character, it'll show us on the right hand side viewing pane over here. So just by experience, I can see that there is a directory, and how I know that there's two directories, and how I know that they're directories by highlighting those 4 lines of bytes there. And I'll quickly explain what these mean in a second once I get the highlighting correct. So again, using these two charts, if we look at the attribute box over here for the first line of code, for the first 32 bytes of information, 1, 2, 3, 4. The fifth from the right is a 0f. What is a 0f? 0f is a long file name. I'll quickly explain what the long file name is. So the difference between a long file name, which is LFN, and a short file name, which is SFN, are that one is a single entry as opposed to the other one. It's just an entry to cover for the remaining file names due to the FAT16 file system limitations. So due to disk technology limitations, FAT16 could only house a maximum file name of 8 characters with 3 characters reserved for the extension type. So this was known as the 8.3 naming convention. So to be able to store file names which were longer than 8 characters, Microsoft re-engineered FAT and developed FAT16, which is the one that we're using, which could house a longer file name by means of taking up entries in the data area of files to be able to store a file which had a longer name, also known as a LFN, long file name. This would take up the required number of entries depending on the size of the file name and the data area. So if the name exceeded 12 characters, 8 for name and 3 for the extension, a new file name would be made and the attributes would show up as a LFN, such as the one we're dealing with right now. LFNs can be applied to files and directories. And now that we know the difference, we can continue to find what we are actually needing to look for. So when you need to deconstruct attributes, you want to actually access the short file name as opposed to the long file name. So with the 0f, I'm doing this by experience again, so I'll try to go a little bit slower. So when we use this template, it's the 1, 2, 3, 4, fifth byte from the right, 1, 2, 3, 4. It's that particular one there. The first two lines were the volume label because it was 08. 08 is a volume label. And remember, each entry is 32 bytes long. So every time you want to work with a entry, highlight the 2 lines of code, because once we set the Bless hex editor in the first video to 16 bytes per row layout, 2 lines would equal 32 bytes. So I'm going to highlight the second 2 bytes, second 2 lines. I keep calling it code, but it's I shouldn't really be saying data. So highlight these next 32 bytes of data, and then if we take the 5th byte from the right on the first line, which is the attribute, 0f is a long file name. So we need to go, and short file names for that particular long file name will be directly below them. Okay, it's not like they'll be in other areas of the drive of the image. It will be directly below. If that's a long file name, this could also be a long file name, but in this case, because the stuff directory apparently has just over 8 characters, but below 16, so that way it only had to make one long file name entry for this particular directory entry. So if you look at this 10 digit over here, since 0f is a long file name, 10 and the next 2 lines of data, which is the next entry, represents a subdirectory. And that's what we're going to navigate into to see if the stuff directory has any files. And we can kind of see that it's creating a tree, let's say. So the root right now has stuff as a directory, and then it's got a mist for miscellany. So these two are the directories that I can see just in the ASCII viewer to the right. And if you notice here as well, it's the first 2 lines of data show another 0f and then a 10. So 0f again is a long file name, and a 10 is a subdirectory. And you can see that it shows MISC because the first 2, 4, 6, 8, 2, 4, 6, 8, 8 bytes of data represent the file name. In our case, it's a directory name. So I'm just going to be using that information to identify and validate myself that, hey, no, this is what the file itself or the directory itself is called. So without further ado, let's navigate to the stuff directory. So I've highlighted the short file name, which I need to be working with. And I've done so this particular calculation was performed to get here. And what we're going to do now is we're going to be using this particular calculation to be able to go to where the stuff directory is. So I'm going to do this particular calculation now. So start sector of the cluster area. So how do we find that? The starting cluster is on the second line, and it's again 4 from the right, which is occupying 2 bytes. So if we take those 2 bytes, that's what's showing us as the starting cluster. So remember, when we're writing anything from a hex editor, in our case, because we're dealing with the USB image, the way that computers write to the drive is very different to how humans just read the information. It's not just a traditional left to right reading. So when we extract this bit of information, the starting cluster, which is 0200, the way that we're going to have to read it is a term called little endian. And that particular method is not the traditional left to right method. Well, it kind of is, but what we're going to do is for the entire array, you're going to read it from right to left, the entire array. So whatever this, so in our case, the array is 0200, we're going to read it from right to left. But within each byte of data, because remember 2 hexadecimal digits in a hex editor is going to be representing 1 byte of data. So within each byte of data, you're going to read from the traditional left to right, but then the entire array, you're going to read it from right to left. So in our case, 0200 will become 0002. So 00, then 02. And if you were to write this in hex, it'll be 0x2 because you can delete the initial 3 zeros because it doesn't change the value. 2 in hexadecimal is 2 in decimal as well. So we know that the stuff directory starts at sector 2. So what we're going to do with this particular information now is use this calculation here. So start sector of cluster area. So the cluster area from the FSStat output starts at 536. So we're going to go 536 plus the cluster number minus 2. So the cluster number that we're looking at right now is 2 minus 2 multiplied by the number of sectors per cluster, which is 2048 divided by 512. And that should equal to find the offset for. So I'm going to quickly calculate this. So that's giving us a value of 536. And what we're going to now do is that's the target sector that we want. So 536 multiplied by 512, which equals that value there, 274432, which in hexadecimal will equal 43,000. And if we were to take this particular value and paste it here, we can see that so 43,000 just starts just there. So what we're going to be looking for now is another type of validation to see that if we are in fact in the stuff directory. And how we know this is by the first byte of data, which is representing a 2E, which in the ASCII charts is a full stop or a period. And if you remember, when you're navigating around in terminal, the way you move up and down directories is by using the cd ... So if I were to say, where am I? I'm in my home folder right now. So if I were to navigate to cd tilde desktop, and if I were to go cd FAT file carving, that particular folder there, the way that you move back is if you go cd space ... That's how you move a directory up. So notice we went from desktop to FAT file carving, the folder, and then when we use the cd ... it brought us back to the parent directory. So cd ... in this case, when we're looking at the hex editor, is the current directory you're in. So that's how you know that this is now, you're now looking at a directory, and these are the directory entries. And if you notice the next 32 bytes of data, it says 2E, 2E, which is 2 periods. And that's how we know again that if we were to, this particular entry is representing you kind of to go back to the parent directory. We kind of don't need those two at this stage, but these are the validating information that we can use to show that, hey, look, we are in fact in the stuff directory. So if I were to just quickly browse over here, we'll use the long file name, short file name method that we learned in just a while ago. So I can see that there's 0f, 0f. So that's 1, 2, 3. I can see there's 0f there, 0f there, and a 20 there. 20 is an archive, which is a file. So that is considered one file, and it says some sort of ITSM nuggets, some sort of JPEG as far as what I can see. So ITSM nuggets.jpg, that's one file that I can see in the stuff directory. And the next file I can see is this particular one, which shows a 20 straight away, which is saying a FF for a BMP. So I'm just going to name it what I think it is, FF for a BMP. And we can see that there is another long file there, long file entry with the 0f, 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 and then a 20, which shows us that this again is another file, which is apparently it's a schedule report marking report. So I'm just going to say schedule report marking report .doc apparently. we can see some sort of extension being identified there just in the ASCII viewer. So what we're going to know now is we can validate that there's 3 files in the stuff directory that we're going to try to carve out. But let's see if it stops us, because there are a few limitations. So 2E, 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 which is representing the 2 sets of periods. So we don't need those those 4 lines of entries, because those are representing the directory and the subdirectory. So what we do need is the next bit. So what we're going to do is highlight the next file. That's those 6 lines of data, 0f, 0f20. So 0f is long file name. If you keep going down, the short file name will be directly after the long file name, which is showing up as an archive with the attribute value of 20 over here. But why we can't carve this particular file out is because it's actually deleted. And the way that I know this is the E5 character at the beginning of the file name. E5 shows the disk that this particular file is deleted. Because of the security issues with the FAT16 file system, when you even any normal file system, when you format the drive, it only puts a 0, or it shows the file system as deleted. In our case, the FAT16 file system, which is showing a E5, different file systems may have a different mechanism. It's showing as a E5, showing the drive, whatever is reading the drive. In this case, it's the computer, as it's deleted. The file itself is deleted. So the rest of the remnants of this particular file still remain, unless you perform a low-level format. That's when you erase, put zeros into each byte of the drive, and that way all the sectors get filled up with zeros, as opposed to this particular method of formatting. You just replace the initial starting value with the E5, identifying to us that this particular file is deleted, because even the short file name is deleted. So let's look at the next file. Again, it's showing a E5 for this particular archive file. So let's look at the next one. There's a 0f, 0f, 0f20. So this has 3 long file name entries with a short file name, this marking report and schedule marking report. And we can see that this doesn't have an E5 at the starting of any of the short file name or any of the long file names. So what we're going to try to do is we're going to try to carve out this particular file, because now I know that this file is not deleted. So what we're going to do now is we'll be performing these calculations again. And what we're looking for again is to extract the short file name only, the information from the short file name, and we're going to be looking for the start cluster. So the start cluster is 1, 2, 3, 4 bytes from the right. It's those 2 bytes there. So 0A, 0C. So 0A, 0C is what we're looking for, and we're going to perform this particular calculation. So 0A, 0C equals 0, because remember we have to read in little endian, 0C, 0A, which then equals 0x COA. Just going to get this in hexadecimal, COA, which equals 3082 in decimal. So what we're going to do is we're going to use the start sector of the cluster area, which is 536, plus this particular decimal value, because we have to turn this into a decimal value before we perform the calculations, because the rest of the calculation is in decimal value as well. 3082 minus 2 multiplied by 4, because I'm just simplifying this particular value there. 2048 divided by 512 would be 4 bytes, sorry, 4 sectors per cluster, and we should have a value. That's giving us 12856. And what we're going to do now is use the target sector calculation. So target sector calculation will be 12856 multiplied by 512, which equals 6582272. And now that in hexadecimal will equal 0x, getting this value here, 647,000. It's a base 16. That's how we can confirm that it's a hex. And this is where the starting of that particular file is in the data area. Right now we're at line 43120. Obviously 647000 is much higher than this, and we can see that it's actually moving further down the image. But before we go to this particular area, what I want to do is I want to also extract the file size, because what I'm going to do is what you will have to do is, when you're carving out files, you need to know the starting location as well as the size of the file, so that way you know where to stop carving it out. Because if you don't have the full size of the file, you'll be kind of mixing information, let's say, off another file or another pieces of information, which won't actually complete the file, thus not making the file properly execute. So in our case, we want to find out the file size, right? So still extracting this information from the SFN, nothing to do with the LFN as of yet, just the SFN. Those 4 bytes from the right on the second line are the file size. So we're going to use, so this is the calculation for the marking report. File. And we're going to use the file size. And the file size is 00980000. Now we're going to have to read this in Little Indian, which is 00009800, which simplifies down to 0x9800. So now all we have to simply do is, because both of these are in hex, we simply have to add these. So this is the starting location. Since the file size is that much more, we add this to this figure. So if we change the calculator to hex, this is this value. So you plus 9800 and you get this value. So 0x647000 plus 0x9800, which equals 650,800. So what we're going to do is we're going to carve. So the carving portion for that particular report, the schedule report.doc, would be from 0x647000 all the way to 0x650,800. And what we're going to do is we're going to carve out the range between this. Now in Bliss Hex Editor, there is a simple, very simple select range option. If you click on edit and click on select range, or just click Shift Control R, it'll bring up this particular box. And in this box, you want to input the values here, including the 0x in the front. And we want to click select, and it'll automatically select the range where it thinks the particular navigation areas are. So what we have to do now is click edit, copy, and we're going to create a new file within Bliss Hex Editor itself, and then we're going to just simply paste the data. And now we need to know how to save this file. And if you watch my previous videos, this particular technique that I'm going to perform here is actually covered in the file signature analysis, where we take the header and the trailer of the file, if there's one on this case, to analyze and decipher what particular extension to save this file as. So what I'm going to do is I'm going to take the first few bytes until it reaches 0. I'm going to copy them, and I'm going to go to this particular website over here that I have opened. It's called Gary Kessler. This particular person has obviously taken their time into having this category and this directory of all these headers and trailers that we can use. So all thanks obviously goes to this person. And we use this website and just use a simple find function, which is Control F, and then we paste the value that we've extracted from there. So as you can see that this matches exactly. So This matches exactly all the way from DO to E1. And this is identifying as several Microsoft Office documents. So this is like a compression document. So there's a .doc, PowerPoint, XLS. And what we're going to do is I'll try to save it in the .doc first and see if saving it in PowerPoint or Excel spreadsheet makes a difference. And I want to save this particular one into the results. I'm going to save it as one.doc. Actually, no, I don't know what those files. I'm going to save it just on the desktop. One.doc. And I'm also going to save it as one.xls. And another one in the PowerPoint format. So those three are there. So I'm going to open the Excel one first, and you can see that it opened straight away. And it's showing up as a marking schedule of some sort. To be honest, that's my course code that I had done in my degree, but the date is very different. But at least you can see that this is carved out entirely from the information from that Bless Hex editor before. So that particular information was just carved out, and we found the means of the starting file and the starting location of the file and also the ending location simply by adding the size of the file to the starting location. And I just want to open and see if this file shows as anything different. If you open it in PowerPoint, PowerPoint's not working. I want to open it in Word. Word opens it fine as well, but it's the same thing. So that's going to conclude our investigation. So I hope I wasn't going too fast, and I hope you guys understood everything so far, as this brings us to the end. And if you wanted to continue carving more files, simply use the method that I've shown here. I know that this particular category of manual file carving is lengthy, but it does take some time to explain the surroundings and why and what I'm doing before actually doing it. Please like this video and watch my other videos for a better understanding. And also, like I said, this particular method that I use to find out what this file could be is called the file signature analysis videos. There's a category of videos in my digital forensics playlist. Check those out because they kind of show you different file formats and how you can identify what those files are. There's another forensic scenario there as well. And if you have any questions, ask in the comment section, and either I or the community will be able to help you with your request. I'll leave all the links to the images as well as the USB image and the website link for the file signatures, as these are crucial for the data extraction. And I'll also leave all these images as well as this image. That was a differentiation before. And in the future segments of the FAT file carving, I'm going to show you guys how to rebuild cluster chain. So that way we can, we can carve out the deleted files, which were these ones over here. Because these ones, if you go to this particular location and try to carve it out, the data won't be accurate, and the remnants of the file may not be accurate either. But by rebuilding a cluster chain, what we can do is we can mount this image as a whole image and then practically navigate through the image as if nothing was ever deleted. So I guess stay tuned, and thank you for watching.